And so before I turn it over to Ashley, a few announcements to start. If you find value from this tutorial series, or if you have any suggestions for things we should change in the future, please use this QR code on the left to leave us any feedback. We value your opinions and feedback, especially those of you who have been to a few of these. And so please let us know what we should continue doing, or maybe if we need to change something in the future. The middle QR code will take you to a GitHub page for the entire tutorial series. And to find the materials that Ashley will be using today, just go to the last folder with the numbers corresponding to the date for today's tutorial. And if you're not already a member of GDS but would like to become a member, you can scan the QR code on the right to be taken to the form to fill out to join GDS. If you are already an APS member, then joining GDS is just a $10 fee on top of that. If you have suggestions for future speakers or future topics for this tutorial series, please feel free to email them to me, and you can find my email address at the top right corner of the screen. Our next tutorial in the series will be in 2 weeks, so on June 20th at 1 p.m. Eastern Time, and it will be on physics-informed neural networks and neural differential equations. You can register for this tutorial at the same link you used to register for this tutorial. And if you're unsure of how to do that, just type GDS Engage into Google and click on the first link, and that will take you to the page to find the registration links. This is the 6th tutorial in the series. And if you want to view any of the recordings of the previous tutorials, we have them posted either on the GDS Engage webpage here, and you can scan that QR code on the left, or you can go straight to the YouTube playlist by scanning the QR code on the right to view all the previous tutorials on things like APIs and unsupervised machine learning. And then as a final announcement, GDS has recently started a paper highlight series. And so if you are especially a graduate student, a postdoc, or an early career member who has recently published a paper that you think would be beneficial to the data science community, please scan this link and fill out the form, and we would be more than happy to highlight your work on our website and also on our social media accounts. And so with that, I will stop sharing. I will turn it over to Ashley.
Thank you so much, Julie. So hi, everyone. I'm Ashley, and I'm a postdoc at the University of Toronto. And because we do need to download some data for today's tutorial, before I get started on the slides, I'm going to walk through the first few steps of how to get things set up on Google Colab. And then once we get the data downloading, I'll start giving the background information that we need for today's workshop. So Julie has just put the link in the chat, and I'm going to go ahead and share my screen so that you can all see what I'm going to do. Let's see here. Gotta get the right one. All right, so you should be able to see the GDS tutorials here. We go to the uncertainty quantification one. You can open up the uncertainty quantification notebook, IPyNB, and then hit open in Colab. So that should take you to the Google Colab. Now we're going to make a few quick changes to this. So if you see this file icon on the left, we're going to open that up. And we need to make sure that our environment has these things that yours does not. So the GDS tutorials, and then these files here. So I'm going to show you how to get them. The first thing we need to do is hit a new code line here. All right. And then if we, can you still see my notebook page here?
Yes, we can see it.
Cool. So I'm going to take the link from the main GitHub page. I'm going to type exclamation mark, git clone, and then that whole URL for the main page there. All right, and I'm going to hit the little play button. It's going to give me an error because I've already downloaded it. But for you, it should start downloading the whole repository onto Google. Now, this is not downloading to your local computer. It is still on the cloud. So you're not going to be able to keep any of the changes that we see here, just as an FYI. Once that's downloaded, you should see a directory that looks like this, GDS virtual tutorials on the side. You're going to open that and go to today's, the uncertainty quantification, open that, and everything except the README, you can just drag and drop to the top level. So all of the files inside here, that's what you're going to drag and drop into your Google Drive. Give people just a second. And if you can put a thumbs up on your name in Zoom when things are working for you, that'll help me know when to keep going.
Can you show where the download button is again, please?
The download button is this right here. So I took the main GitHub URL from the main page here. And I'm just copy pasting this into the cell at the top of my notebook with this git clone command right in front of it. And then I'm pressing the file icon on the side, and this GDS virtual tutorials directory should show up for you. How are we doing? Is the cloning working?
Sorry, at one point you moved some files from someplace to someplace else. Can you repeat that?
So sure, right here in the GDS virtual tutorials, this directory should have things inside of it. Everything inside of that, you can just click, drag and drop to the top level here.
Okay. Thank you.
So here's the file inside. And I'm just moving it all the way outside to the top level. You need to add the GitHub link yourself. So in order to do that, you hit the code button right here. And you literally type this command, !git clone, and then the link. Just like that. To get the file tree on the left, you're going to hit this file icon. And it should just pop open for you. All right. How are we doing? Give me thumbs up, happy emojis. Are we at this point where we've got it cloned and we've got our files in the top level here? So to get the files on the left, you see this little row of tiny icons. You're going to want to hit the file folder icon right here to pop it open, and it should turn orange. Have a little orange line next to it. Little repository not found. So you can also try doing it with this command, and I can put this in the chat. So now you can see it's saying that my value is already there. All right, so everybody should have this line at the top. Once we have this line at the top, it should download. It's not going to download for me because mine's already downloaded. Now we need to do two more things. We need to do an exclamation mark and then say pip install, and you're going to install two packages that are not already in Google Colab. So the first is PyMatGen, and we're going to run this cell. It should start installing it for us. And then the second one that you're going to do, and I can throw this in the chat. We're going to do pip install Shapely. And I think that should be all that we need to get off to the races. All right. So once those two things are done, you're going to run the matplotlib inline, and then you're going to run the import statements. If all of your code files are at this top level here, this should run without any issue. And then we're going to try and get our data downloaded. So we're going to download the data pickle. And you can see it's got about 211 megabytes to download. So this is going to take a few minutes, and we'll let that run in the background while I start talking about what we're actually going to do today. All right. Any questions on this part? Last call before I switch to slides. Sweet. All right, switching over to slides. So, as I mentioned, I'm a postdoc at the University of Toronto, and my background is actually in solid state physics. So I used to do some magnetic materials stuff. And then I also started getting into machine learning and the neural networks. But something that I do now is material science research. And so part of this is going to be coming from a material science background, just because uncertainty quantification is a really big deal in material science. But everything we talk about today can apply to any type of data science method, whether it's a neural network or a random forest type model, which is what we're going to use today, or even just simple linear regression type work. So let's see. So what we're going to go over is basics of uncertainty, and hopefully this is going to be a review for most of us. So kind of what we're going to be talking about. We're going to go through an uncertainty characterization workflow, the things that we actually want to do when we're looking for uncertainty. And then we're going to do a case study that's going to use our Jupyter notebook to actually show how are we going to apply these ideas to a trained model. So the example I'm going to give is from materials property prediction, but I encourage you to take a moment to think about your case, right? Where would you want to start quantifying the uncertainty in your data science practice? In materials, we have this idea that we're looking at lots of possible different combinations of atoms in different phases with different chemistries. And so we have a huge chemistry search space, right? And then inside this search space, we have different properties that we either want to use as features in our modeling or we want to predict them. Right, so we have the feature identification stage where maybe we're looking at the band gap of a material or the number of valence electrons. But these are actually physical things that we need to somehow encode in a step, right? That can be used numerically. So this feature embedding step is very, very important. And then once we have a numerical representation of these physical quantities, we actually want to use a predictive model to try and get some new information out of what's going on. But the idea here is that each one of these steps has an uncertainty associated with it, right? How do I know I'm looking in the right range of chemistry compositions? How do I know I have the right features that I've selected from my model? How do I know I've chosen a good representation of those features? And how do I even know I've chosen the right model? Right? There's uncertainty associated with each of these things. So now I'm going to ask you a question and go ahead and think about it for a second. But do your model parameters have uncertainty? And do your data points have uncertainty? So if your model parameters do not have uncertainty, if you are absolutely confident in the number that you have plugged into your system, you might be using frequentist statistics. All right. And there's a lot of work that comes in this paradigm, but the idea is that the reason you have zero uncertainty in your model parameters is that you have an infinite number of samples, right? And so your data distribution, you can keep sampling from it to drive down that uncertainty. And that gives you methods like confidence intervals, significance testing, hypothesis testing, but ultimately the uncertainty is a property of the data. All right. However, if your model parameters do have uncertainty, right? Congratulations, you're probably in the Bayesian statistics regime. So the idea here is that you are going to keep increasing your number of samples, but it's based off of previous knowledge. You don't have that infinite range of data to sample from anymore. And so what you're trying to do is pick very carefully your next thing to drive down the uncertainty, but the uncertainty might never be zero. And therefore your model parameters are always going to have some uncertainty associated with them. All right, so now your uncertainty is a property of the model. And to really drive home this point, I'm going to explain a joke to you because I'm that funny. But the idea here is we have some scientists, all right, and they're going to do an experiment. So they have this neutrino detector, all right, and it says the neutrino detector measures whether the sun has gone nova, all right? It rolls 2 dice, so it does a measurement, and if they both come up 6, then it's going to lie, otherwise it tells the truth. So they roll and the detector says, yes, the sun has gone nova. So the frequentist statistician is going to say the odds of both getting 1/6 is very low, right? Therefore, it's unlikely to lie to us, and therefore it's telling the truth. So we're going to say, yes, you know, if the sun has exploded, we're dead. The Bayesian statistician is going to update their prior. And because if the sun exploded, we would all be dead. And obviously they're not dead. The Bayesian statistician is going to say, bet you it hasn't exploded, 50 bucks. So this is the difference between likelihood and probability, right? We have an updated prior in probability that we don't have in likelihood. The big asterisk on this comic is that it was super controversial in the statistics community. The truth is, if you're doing a good job with statistics, you should get the same answer, whether you use frequentist or a Bayesian approach. But it's a great read, and it's kind of a good way to put a label on how we're thinking about things in these different data regimes. Now, if neither of these two regimes felt like a good fit for your problem, then congratulations, you're probably doing machine learning. Because machine learning is using ideas from both of these. And the truth is most of machine learning practitioners, they just do what works. They're not usually tied up in a lot of the ideas of where is the uncertainty coming from and how are we going to address it. So the challenge if you're doing machine learning type data science is that uncertainty is everywhere. Some things will work, some things won't. But we still need a principled way to approach these problems.
Oh, there's a hand up, Ashley.
Yeah.
Can you hear me?
Vivek, do you have a question for me?
Oh, we cannot hear you.
Can you throw them in the chat for me? That is an excellent question. So the question is, isn't a frequentist just a Bayesian with a Dirac delta? I don't know. I'm not a statistician, so I wouldn't feel comfortable saying yes or no to that question. If somebody else has an opinion, feel free to chime in the chat. All right. So coming back to what we're working on today. When we're thinking about uncertainty doing machine learning, we need to consider different sources of uncertainty, right? So like the material science example that I gave, we have uncertainty from the data, we have uncertainty from model parameters, from optimization choices, from model choice, from the hyperparameters you might use to train your model. But then there's also this idea of uncertainty we can fix and uncertainty we can't fix. And then there's acceptable uncertainty and unacceptable uncertainty. So different kinds of uncertainty. I love this picture because it really does a great job making clear what's going on with different kinds of uncertainty. But you can see I have this data series. And for this region here shaded in red, my data is very noisy. And in order for my model to fit this data correctly, the model itself is not a flat line, right? It has some confidence interval, and that captures the noise of the data by having uncertain model parameters. And so we can say that the aleatoric uncertainty here is noise that is in the parameters due to noisy data, due to these things that basically we can't fix. All right, over here on my left, we have this regime of missing data points, but it looks like we should be able to draw a straight line and fill it in. All right, we can make a pretty good guess at what should be going in this space. That's epistemic uncertainty. We don't have the knowledge, but we're pretty sure what to do. And if we got those data points back, we could fix it, right? Here, adding more data points to this region is not necessarily going to make the model fit the data better. It's still going to need to have some uncertainty to hit these noisy points going on. So the total uncertainty is going to be the sum of the aleatoric uncertainty with the epistemic uncertainty. We want our model to perform well with both kinds, but we can really only fix one of them, right? We can't necessarily denoise our data all the time, although I'm sure there are cases you can. We don't want to assume that we have that case. The epistemic uncertainty, though, we know we can fix by adding more information. So if we have different kinds of uncertainty, what that's going to get us to is different kinds of uncertainty measurements. All right, so going through these one at a time, and I really highly recommend this paper, Methods for Comparing Uncertainty Quantifications. It's very applied. It does a great job breaking down exactly how to calculate these things, and there's also a GitHub repo associated with it. So we're going to borrow some of their code for today's workshop. So the first is the idea of accuracy. All right, so if you look at my x-axis here, this is the true value. The y-axis is my predicted value. If my predicted value matches my true value, this should all lie on a straight line, right? It's the identity function. And so a more accurate model will have more points exactly on this line. And that's what these two are showing here. Here, the points are very close to the line, so it's accurate. Here, the points are farther away from the line, so it's inaccurate. The next one we're going to look at is sharpness. Okay, so now we're going to think about each of my points has some variance associated with it, some error, some uncertainty. The idea is that we want the predicted uncertainties to be small. We do want our model to be pretty confident on what's going on here. All right, so the idea here is that this distribution should be shifted to the left, where this is closer to 0 and this is larger uncertainties. We want sharper uncertainty distributions, smaller error bars. And so that's what this is showing here. Very uncertain, more certain. But, okay, and there's a very big caveat here. We want our uncertainty distribution to also be well behaved. And this is actually one of the areas for uncertainty quantification that is having the most development and research, particularly for regression models, because there's an idea that if we have an error bar, we want our true prediction to be inside of the error bar. So we want all of our error bars to cross over that identity line. Right, and here you can see we do. The error bars follow the identity line, so that true prediction value is somewhere within the uncertainty. This model, that's not the case. We have a lot of error bars that don't touch that identity line. And so even though we have an uncertainty estimate, the uncertainty estimate is not reliable. So this plot here, it's a little bit weird to think about, but basically you're looking at what is the expected uncertainty distribution. All right, so in an ideal case, you're going to have training data that already has an uncertainty associated with it, so you know what the true uncertainty should be. And then you can ask your model to predict what the uncertainty is and compare those things. And so the farther away from that identity line tells you how calibrated or uncalibrated your uncertainty estimate is. So big point here, you want your true value inside of your error bars, and you want your uncertainty distribution to be well behaved, which gets us to this last one, dispersion. So here we have two different distributions. We have a blue one, which is broader, and then we have an orange one, which is skinnier. In general, you want your error bars to be about the same size. You don't want a group that has really, really big error bars and another data sample group that has very small error bars. So the idea is that a less dispersed distribution, like this one, is actually better. All right, so we have an idea of uncertainty. We have an idea of different kinds of uncertainty. We have an idea of how to quantify these different types and measure them. Now we need to actually get into how do we incorporate this into our workflow.
Real quick, Ashley, there's a question in the chat. Is bad calibration the same as missing behavior in the model?
It can be, it depends on the model. So I think the best way to think about it is missing behavior might end up being represented as prediction error, right? So for example, if you think about your model as an operator, it might just put all of your data into one point, one place in the prediction space, and that could still be missing behavior, right? It's not able to correctly generalize. However, you can extend the idea a little bit into the idea of uncertainty calibration. But I would consider the uncertainty calibration to be more that it's learned incorrect behavior, not necessarily missing behavior. It's kind of mushy language, but I hope that helps. So uncertainty characterization. We've already gone through this first step here, which is looking at where is uncertainty coming from. And then the next thing is thinking about where can we actually measure this, right? Within your design workflow, are you going to try different model types? Are you going to test your different types of features? Where are you going to try and measure it? Once you've figured out where you can measure it, we're actually going to do the measurement. We're going to quantify it. All right. We need to see how good of a job our quantification method did by calibrating the uncertainty. And then finally, we can analyze it. We can say, this is the good uncertainty, the bad uncertainty. Is it acceptable? Are we happy with how uncertain things are? Is it well behaved? All of those things. However, quantifying uncertainty requires that your prediction has a distribution associated with it. And not all regression models are going to give you a distribution of values for each prediction. Which leads us to the state of the art for quantifying uncertainties. So in general, if you're trying to get a distribution of predictions in your modeling, you can do it three different ways. The first is the idea that you play with the hyperparameters, right? So maybe you're playing with different kinds of models or different initial random seeds, but you're going to create a whole set of independent models, and each of them is going to give you some prediction, and that is going to give you your distribution. The good thing is you're going to understand where your design choices are playing a really big role. But the bad thing is that it's very computationally expensive and it's a huge search space, right? You have lots of different things to look at. The second approach is to use a model that has a built-in uncertainty estimate. So for example, you have a standard linear regressor, right? And you can get it to predict some output value. What you can do, a very common trick, is to actually add a second output to that and ask it to predict the mean and the standard deviation of your data, right? And so in this case, your training data would need to include a standard deviation, and now you're teaching it to predict a standard deviation, and that's how you're going to get your distribution. So it's intrinsically predictive of that distribution. The third option is that you have a model that's already trained, it's already done, but doesn't give you a distribution. So you actually need to post hoc add something on that will give you that distribution. The good thing is it works with pretty much any model. Methods exist, but the bad thing is it almost always correlates with a decrease in model predictive performance. So your accuracy will go down. Some samples will quit behaving well. So all pros and cons are going on here. These two papers do a very good job giving an overview. Highly recommend them. And there's also good GitHub repos available that show these implementations. All right. So keeping this math light because I want to get into the coding. Total variance for a single sample, we all know this. You're going to have your target value, right? You're going to have your predicted value, and you're going to have n predicted values that represent your distribution. This will give you the variance of them. Very straightforward. But now what we're going to do is we're going to draw on that idea that the total variance can be decomposed. All right. So we want to do that because we want to know how much can be fixed, right? And where is it coming from? So if we can break the total into these two parts, then we can actually improve our model's performance on things that we haven't seen before potentially, right? So the epistemic uncertainty, I've got another cartoon up for this. The idea here is that we're taking our regular total uncertainty, right? And here the person saying, hey, we had 74% effective with confidence interval, 63% to 81%. The epistemic uncertainty attributes that to George, the data tamperer, right? And so we have a single source for that uncertainty. In a mathematics sense, and this is coming straight from ANOVA, we have the mean of the predicted values, and then we're going to get the variance of the predicted values with respect to the mean. So the total looked at the variance with respect to the true value. The epistemic uncertainty is looking at the variance with respect to the mean predicted value. Aleatoric uncertainty is almost impossible to just mathematically predict on its own. There are very special cases where you can, but in general, because it can't be minimized and you don't know what it is going into the situation, you don't know how noisy your data is, you don't know how random your optimizations process is going to be, they'll do it through subtraction. So we'll take our total variance, our total uncertainty, subtract the epistemic, and we'll get the aleatoric left over. Now, the way you know that this process works is that it should always be constant or increasing as you give more epistemic information, right? So as you keep giving your model more information, the epistemic uncertainty should go down. The aleatoric uncertainty should stay the same or increase. All right, we're almost to the part where we're going to start looking at the code again. A few more things to cover. Uncertainty calibration. So we talked about this a little bit with the main slide, but it's really worth driving home that good error bars are an outcome of calibrated uncertainty. They do not guarantee calibrated uncertainty. All right, and so taking time to check and make sure that your uncertainty distributions match what you expect is very, very important part of the process. I have a few resources here, and we're going to follow one method in the code. But for regression models, this is still kind of an open problem. Everybody's like got their favorite way to do it. The important thing is that the assumptions that you're making for your regression calibration match your data. Whether you're choosing a specific distribution of variance that you are expecting to measure, whether you are what relationship between your variance and your error, right? Because remember, we want high error to have high uncertainty, right? And that gets us closer to that predicted value, but exactly how you're going to measure that correlation will vary. So the method I'm going to give in the code, it's there for your reference and it'll kind of show you where it fits in the process, but it's not definitive and we're not going to go through it in detail. The best paper I've found on this so far is this one right here, evaluating calibrating uncertainty prediction and regression tasks. And then these two links, which I'm happy to share, give a good kind of hands-on approach to doing this. All right, pause for questions here before I go into how we're going to run the experiment in the code.
I have a question. There's a thing called error in variables where things that when you're doing a regression problem, the thing on the horizontal axis is assumed to be known precisely. Can you say anything about the relationship between that issue and what we're doing today?
So if your x-axis variable is known precisely, that's going to help you do your variance decomposition, right? In that case, it's no longer going to be a problem with your training data, right? It's going to start being a property of the model, of your hyperparameters, all of that stuff. Now, that doesn't mean that you can't still have epistemic uncertainty, right? For example, you may need additional perfect data points to help drive the error down and decrease the overall noise coming from other parts of your optimization process. But I think that's where the main contribution would be, is you can rule out a source of error during this uncertainty process. Does that help?
I think so. I'll think about it.
Okay. All right. So setting up today's experiment. We're going to use a data set. It's called the Jarvis 3D DFT data set. And basically this is material science data set. It has a whole bunch of property descriptors, like the band gap of a material and the chemical formula and the number of atoms and the energy of formation. All of that good stuff is inside this data set, and it also is very comprehensive. It's large. It has about 75,000 samples, which is why we need to start downloading it at the beginning of today's meeting. Because it has so much data, we're going to do this kind of trick. We're going to choose an element from the periodic table, and we're going to take samples that contain that element. So example, if any element in this, or if any sample in this data set contains the element iron, we're going to not train the model on that and hold that into our test set. So our train set is going to be in distribution, and it's never seen iron before. And then the out of distribution data is going to contain every sample that has iron in it. Then we're going to train our model. And today's model, we're going to do random forest because it's fast and it's really good at doing an ensemble method. And we saw earlier that if you have an ensemble predictions, that gets you a cheap prediction distribution. And we're going to ask the model to predict energy of formation for this materials. All right. And so the idea here is that the model's never seen this element before. The model's never seen chemistries that contain this element, but can it still predict the correct energy of formation? Now, my friend Kang Ming did this in a paper, and it's a very cool paper. I highly recommend it. Now, what he found is that the model can do this. It can generalize and predict that missing element with different success. So the yellow ones here show every single place where the model could predict the energy of formation for a chemistry containing the element that it's never seen before, except for these ones right here. All right, so the R squared value for fluorine is 0.148. On the upper side here, we have 0.636 for beryllium. And so the interesting thing is whether it can generalize or not depends on what information it was given. We have a case of epistemic uncertainty and epistemic error. It couldn't generalize because it was missing those formulas. So what we're going to do is we're going to play with this idea a little bit more and see how that's going to break down in our uncertainties. Now, you can see here, I have a random forest and I've omitted fluorine from training. So I've omitted an element I expect it to perform badly. All right. This is the number of estimations that I have, the number of trees. So every tree in my random forest is going to give me one prediction from my distribution of predictions. And then I'm going to look at my R2 score as my error metric. And ideally, what I would like to see is that as I have more predictions, right, my error goes down. But that's not really the case. For my training data that doesn't have fluorine, I get perfect score right away, right? And then for my testing data that does contain fluorine, it's just bad. I mean, it's terrible. So here we're saying that it's likely to have high epistemic uncertainty just from knowing what's going on with our error metric. However, if I do one of the yellow boxes, a good element, so this is iron. Now the model has never seen iron during training, but iron is all in the test set. My R² score is really, really high. So this is 0.88 compared to minus 0.6. And you can see that there is a little bit of a boost by giving extra trees, but then it kind of flattens out. So here we can say that it has low epistemic uncertainty. Do these ideas get supported by the math that we looked at earlier? And the answer is kind of. So now we're doing that variance decomposition. I have aleatoric estimates and I have epistemic estimates, right, from my total uncertainty that I can measure. And you can see here, when I omitted fluorine, my aleatoric uncertainty actually stayed very, very constant, even though I was giving it more information, right, more trees in the prediction. For the epistemic uncertainty, a little bit of an interesting trend, right? It goes down and then it kind of goes up for the testing, right? So now as I'm adding more trees into my model, it's doing a better job generalizing after a bit when it gets more. It's more straightforward for the training data, right? More trees helps the training data just directly, and that makes sense. However, for the case where I had iron, right? So this model actually performed well. The uncertainty decomposition is much messier, right? So we can see here my aleatoric uncertainty is flat for the train pretty much, but for my test, it actually has this orange curve. And so this is telling me that the variance decomposition doesn't do a good job for this task. There's something else going on. The assumptions that we made back earlier, they're not good ones for this problem. Now we know that because the aleatoric should only stay the same or increase, and it's not having that behavior. So this is my little plug into why you should still be considering this. You can actually use this decomposition to help guide your future experiments, right? So in this corner, we have samples that have high epistemic uncertainty and low aleatoric uncertainty. And so if we were going to try and give our model more information, we want to give it these data points, right? This is where we should be looking to continue training our model, because this is where we can say more information is helpful and we're not just adding more noise. And that's kind of why this is useful. All right, we're almost at an hour here. So we're going to switch to the coding exercise in just a second. But the idea here is that we're going to choose an element from the periodic table. All right, and you can choose anything that you like. They're all in there. We're going to track the uncertainties as the model gets larger. So we're going to keep adding trees, and then we're going to observe the separation between the uncertainties and also the calibration error, because I left that in there. So that's kind of our play space and where we'll start looking at what's going on and how the system is behaving. A quick thank you to my collaborators, Kangming Lee, who's the genius behind the first paper that kind of kicked this work off, and then Brian DeCoste at NIST, my group here at the University of Toronto, and my advisor, Jason Hattrick-Simpers, and then more good papers to recommend because they really helped me as I started digging into this. All right. Questions while I switch over to showing the notebook. And the statistical literature, you can look up measurement error models. Oh, thank you for this great comment, Christopher.
Okay, I do have one question. Random forest has other parameters like the M-try parameter, not just the number of trees. Did they try varying M-try and other fitting parameters in random forest?
So for that paper, they did not, because the goal was really to hold all of the hyperparameters that they could the same and then see how the data played in. So it was very much a study of the epistemic uncertainty.
Okay, thanks.
Sure. All right, so from here on out, we're going to be looking at the code and the notebooks. If you are happy with your understanding of the code, feel free to drop off at any point. And if you have questions, speak up, throw them in the chat. We'll get this going. All right, so hopefully you will be at this point where you have the data downloaded. So we're going to go ahead and read the data pickle in. We have that 75,000, 76,000 data points and a quick inspection of the data frame. You can see what we have to play with here. So we have sample IDs, SPG symbols, numbers, formula. This E form is our formation of energy. We have band gap, the atoms in the lattice, all this good stuff going on. So for the first one that I'm going to run, we're just going to do the target as E form. I'm going to say, give me all of the data. If your system's a little bit slower, you can pass in fewer samples. So example, make this number 100 or 1,000. And then the element that I'm going to emit from the training data is iron. I'm going to pass that in and get my samples. Divide it into test and train. All right, so I'm going to start with a smaller forest here. I'm just going to start with 5 trees to make it go quickly. I'm going to define my model. We're going to fit it. And we're going to ask it to predict on the training data and predict on the testing data. So this is going to give us our average prediction pretty much, but we can also do it on a tree by tree basis, which is what this next part is doing. So for each tree in my model, we're going to get the predictions from that tree for the test data and the predictions from that tree for the train data. We only have 5 trees, so it goes really, really fast. And then I'm going to get the set of all my predictions, and this mean value here should actually be the same as what I predicted using just this straight up predict function. I'm going to do that for my training and testing data. All right, sanity check time. I want to create that plot that looks at the accuracy of my data. So I'm going to plot the true values against the average predicted values. And then this dashed line here is the identity line. So this is the line where I want all of my points to lie on top of it. You can see it does a little bit better for my training data. It's got an R squared of 0.99 compared to 0.96 for my testing data. But the testing data has that element the model has never seen before. So we're still very happy with this as far as a model goes. Now we're going to do that total variance estimate for each sample. So we've already got the code in here. Just going to run it. Now you can see the difference in size between my data sets. So there's almost 72,000 training data samples compared to 4,000 testing data samples. When I'm calculating my epistemic uncertainty, because I want to do that variance decomposition, all right, I'm going to use the same function, but now instead of passing in the true value, I'm going to pass in the average value of the predictions. And then to get my aleatoric uncertainty estimate, I'm just going to take the difference. So checking the model calibration, I'm going to see how did the error do. So this is just how far away is my predicted point from that dashed line. And then I'm going to get my error bars to go with it. This calculate calibration function is coming from the method that I mentioned in the one paper, but basically it's trying to say, is that distribution of uncertainties that we just calculated well behaved, and does that distribution include the true value? So that's what this function is doing. The next thing we're going to do is just look at two different metrics. So this calibration error is looking at how well our uncertainty distribution matches a normal distribution, because that's what I've chosen for this problem. It doesn't necessarily mean it's the correct distribution, it's just the most common. And then the other thing that I'm asking it to do is look at the area difference between these two curves, which will make more sense in a second here. So on this plot, you can see this dashed line here is my calibration model, right? So this dashed line is saying that the errors that I've expected to see and the error that I observed, with the uncertainty that I expected to see and the uncertainty I observed, do they agree? And that's the dashed line. The curve is showing what the model actually predicted. All right, and so you can see that when I expected an uncertainty error combo, because I'm actually using the z-scores in the code here, but when I expected to measure, I actually observed a little bit extra, which is why there's a blue space on top. And then over here in the middle, you can see that I actually observed less than I expected. So the difference between the curve and the straight line is going to be the calibration error, right? And then the actual area between these two lines is represented by the calibration area, or the AUC. So the interesting thing here is that we do see a little bit worse calibration for the model that's for the model on the data that has the element that we haven't seen before, right? It's not predicting exactly the same distributions that we want. It's not as well behaved. The error bars are not as good. So now what we're going to do is we're going to compare aleatoric and epistemic uncertainties. So you can see I just pulled out the standard deviation here. And I'm plotting the standard deviation as the error bars on my plot. All right, so this is the same parity plot here, but now I've just broken things up a little bit differently. For my training data, the error bars pretty much all overlap with that red line. It's looking pretty good. And if we think back to that original slide where it says, you know, are our error bars small, right? Are they all about the same size? Do they overlap and have the true value in them? How's that distribution looking? Is it well behaved? Overall, the training data is a little bit better, just a little bit, than the testing. The testing, you can see there's like a group right here that has really big error bars, group right here that has really large error bars. Same value range, right? Because this is my target. I have a group that has really, really small error bars, and then not too far away, a group that has really large error bars. This is where that difference in calibration error is coming from. So what this is doing is it's pre-predicting. Right here, we can say, okay, we know our uncertainty estimate is not the best because it's not a perfectly straight line. And then when we're coming to our error bars, we're seeing, yeah, these error bars are not as reliable as we would like them to be. Because right here, we can see it doesn't overlap with the true line. We can also do that distribution of the standard deviation. So you can see that the testing uncertainties are higher than the training uncertainties. And that's good, right? We would expect it to be more uncertain on an element that it's never seen before. Overall, it's still pretty low. We have uncertainties that are in the range of the target, and that's a good thing. If our distribution was way up here around 4, when we don't have a lot of predictions to make around 4, we would be worried. And then the last thing that we want to do is that plot that says, can we find samples that have high epistemic uncertainty but low aleatoric uncertainty? And so I'm looking in this low corner, and for the training data, no, there's nothing in this corner. But for my testing data, there actually is, right? We have really high uncertainty in this little space for the epistemic uncertainty, but not for the aleatoric. And so that's interesting. We want to start tracking these things. So this is where I'm going to encourage you to start typing your own code, and let's see if we can make some informative plots about the things that we've observed so far. So I'm going to create a Panda data frame, and I'm going to call this my train uncertainty data. All right, and to do this, I'm going to do pd dot cconcat. Or actually, let's even make this simpler. Let's just make this a list. All right, so the first thing I'm going to log here is my calibration error. All right, and I'm going to do 0.339 for my train. I'm going to make this a list of lists to make my life a little bit easier, and I can convert it to a NumPy array later. Then what I'm going to do is I'm going to track, let's see here, what is interesting. Let's track my average explain variance. So I'm going to add some code that looks at that. You can see right now it's an array. So I'm going to say explained variance is equal to np.mean, just like that. And I actually want to label this as train as well. And I'm going to do the same thing for my testing. And then I'm going to print both of these values. So I'm going to grab this, throw this in here. I'm also going to do the same thing for the unexplained. And I have that as my difference in variances right here. If I could do it. And really at this point, it's just up to you to start playing with the code and start seeing what patterns you can pull out for the analysis. And so this is going to give me my first data point here that I'm interested in. Now what I'm going to do is I'm going to go back up and I'm going to actually choose a different number of trees from my model. So if I go right here, so I had 5 trees. I'm going to double it and do 10. And I'm going to just rerun these code cells all the way down. Did I miss any questions in the chat? See here, 68, still predicting what's going on here. So my calibration error hasn't changed at all. It's 0.339 still. Keep going down. So I'm going to log this again. And then my other two, you can see, now have increased actually. So at this point, I'm probably going to want to start creating a plot. And let's create 1, 3. There we go. And I'm going to have the forest sizes that I've studied so far. I'm going to add something here to just cast my data to a NumPy array. And that just gives me a nice way to index and slice into it. So now if I do my first axis, forest sizes versus, let's see. Make 0 dot set title. So this is going to be my R squared value. And then on my x-axis, I'm going to put the number of trees. My y-axis is my error metric. And then I can continue on for my other things that I'm tracking. But yeah, that's what I've got for you today. I'll stay on for a few more minutes and keep analyzing the data that's easy to get here. But if you don't have questions and you're good with where we are, feel free to email me later. I'm always happy to chat. But thank you so much for making time today. I really appreciate it.